Okay, guys, this is a lecture I discovered that I do not have in my library of lectures for you, so this is what you're going to use for today's assignment and to kind of wrap up what you did with the PDawg over the weekend. So, this is about solutions, and we're going to talk about saturation and solubility here. So what you covered over the weekend was saturated versus unsaturated, and so the idea was that you can have a solution of water. Let's draw our beaker here. All right, and we have our water in our beaker, and inside our water we're going to have a solute in there that's going to be pretty much evenly distributed throughout, and this is called a homogeneous mixture. If we can't see the solute, we might be able to see the effects of it, like maybe color, or it gets a little murky. Well, actually, murky doesn't count because it's not really dissolved if it's murky. But you have the solute dissolved in our solution, and if it's completely dissolved, okay. Well, first of all, if you have the stuff that is dissolving into the water, that means it is soluble. Okay, which means able to mix or able to dissolve. Okay, so if we have something that's soluble, it is able to dissolve into our solution. If it's insoluble, okay, then it's not able to dissolve. And you'll find that a lot of the terms in this unit are opposites of each other. So soluble, insoluble, saturated, unsaturated, that sort of thing. And so if you can keep adding your solute into the solution, if you can keep adding more, then at that point it is still unsaturated. Okay, so from the very moment that you put just a little teeny tiny bit of solute, so let's say you're going to use your Country Time lemonade, and you're going to put a scoop of the Country Time lemonade into your into your gallon jug because you're making it for your whole family. When you put that first scoop in there, and it'll all dissolve, and it'll get yellow, but it'll still be pretty transparent. You'll be able to see through it. When you put all that in there, you know that you can dissolve more into it, but then it's going to get really tart, and you'll have a heavy lemonade taste. Like a whole bunch of them will be really sweet. But until that point, because you can keep adding more, you're going to have an unsaturated solution. You can still, or it is some amount less than, you have a solute level less than the maximum possible to dissolve. Okay, so you can keep adding the stuff and keep adding the stuff, and as long as you can keep adding it, it is unsaturated until you start getting the solid collecting at the bottom, and no matter how much you stir for that particular amount of liquid, you can't get that stuff to dissolve. And you can stir and stir and stir and stir all you want, and the liquid is at its maximum capacity, and this is called saturation. Saturation. And saturation is when your solvent, the liquid that you put it in, cannot hold anymore. Cannot hold any more solvent. I'm sorry, cannot hold any more solute. My mistake, solute. In solution. And it leads to a precipitate, or it leads to excess solute at the bottom. Leads to excess solute at the bottom of your sample. All right, now you've all seen this before. Let's see, you load up with your chocolate milk, right? And you dump chocolate milk in there, and you stir and you stir and you stir and you stir and you stir, and you still can't get those last little flecks of chocolate, chocolatey goodness that's at the bottom of your glass of chocolate milk, assuming you're not using a liquid. But the manners of making chocolate milk vary. But if you're using Nesquik stuff, the powdered chocolate milk, you put it in there and you stir and you stir, and you still get the stuff down at the bottom. That is the stuff that just couldn't dissolve into your milk anymore. It was just excess solid that you couldn't would dissolve, and so that at that point for that particular solute, your solution was saturated. Okay, now. How much is saturation? Well, there's two things that control saturation, and there's two parts to, there's really two factors to consider. The first part is, how much is saturation? How much is saturated? How do you know when something is saturated? Okay, so how do you know when something is saturated? Well, that's a tough question because you can't really know when something is saturated until you've gone too far. Because as soon as that first particle, that first little crystal of stuff that you're trying to dissolve, you see it at the bottom of your container and you can't dissolve it anymore. Well, there you go. You have a saturated solution, and you've gone a little too far because you have a little extra solute in there. Okay, so how do you know when something's saturated? Well, you see excess solute. But what you can do is you can measure this, and you can find that amount of solute that you've dissolved for every, say, 100 grams of water. Okay, because if you double the amount of water that you're dissolving, then you can double the amount of solute you have. There's just more water in which to dissolve all your stuff. And if you have less water, then you can dissolve less. But it can be proportional to the amount of water you have. All right, and this amount of solute per 100 grams of water, you might be able to see, you might have already noticed, is up here on this table. Grams of solute per 100 grams of water. And it's different for every solute. They each have their own point of saturation or level of saturation for their 100 grams of solute. And so we create these curves based on how much... actually, we have a label missing down here that I must have cut off. So we'll fix that here in a minute. Okay, so I'm going to show you guys how to use this solubility curve and how to apply it to your homework. So let me turn that off. Use this layer. So what we should have down here is a layer that says this is temperature. Because this is the other factor that affects solubility. Because molecules move faster, the higher the temperature is, the easier something is to dissolve, and there's actually more space in between the molecules in order to allow more solute to dissolve into that, into your solution. So what we're going to do is, let's say we have, and I'm just going to ask you some questions on it. No, let me explain this first. And we'll take this one right. We'll take this NaNO3. All right, so we'll take sodium nitrate. We'll start with sodium nitrate. NaNO3, known as sodium nitrate. Okay, that's right here. Okay, and if you notice that this follows this curve right here. And so the way we read this is if we have a sample of sodium nitrate in a 20-degree solution, we'll call it right here 20 degrees. Okay, how much can it dissolve? How much sodium nitrate, how much sodium nitrate will dissolve in 100 grams of water at 20 degrees Celsius. And down here is our 20 degrees Celsius. Temperature in degrees Celsius. Okay, so we're gonna here's our 20, and we're gonna follow 20 all the way up to the curve. Okay, and this curve right here is where this point reads to over here on our grams of solute. And so at 20 degrees, we can dissolve, looks like about 88 grams of NaNO3 will dissolve in 100 grams of water at 20 degrees Celsius. Okay, so let's try this again. So what happens if the temperature increases? Now, by the way, this 88 grams of NaNO3, if we add 88 grams of NaNO3 to our 100 grams of water, what kind of a solution do we have right here? Okay, this solution right here is a saturated solution, because this is how much we can dissolve in the 100 grams of water. If we go, say, 90 grams of sodium nitrate, we're up above the line, and that's more than what we can dissolve. And so that difference, that difference between the 90 grams that we put into it and the 88 grams that'll dissolve, that extra 2 grams is going to precipitate out, and it's going to be the excess solute that we find at the bottom of the sample. Okay, so we've created a saturated solution, okay, with some excess solute at the bottom. Okay, now what would happen then? What would happen if we increase that temperature What happens if we increase the temperature to, say, 40 degrees Celsius? All right, so we go from 20 over here to 40 degrees Celsius. Well, that shifts our solubility. We track that up at 40 degrees Celsius, and it goes all the way to here, and that marks out right there that that looks to be like 104 grams. Okay, so by increasing the temperature, we can now dissolve more solute. Check that out. Okay, because we follow the curve up to our new saturation point, because the temperature has increased. Now, this difference comes from an increase in the temperature. Now, what do you think would happen if we lower the temperature again to, say, 30 degrees? So now, let's decrease the temperature to 30 degrees Celsius. All right, so if we decrease the temperature to 30 degrees Celsius, so we slide back down here to 30 degrees, now it looks like it's at 97 grams. Okay? So that's how you read our solubility curve. And we're going to work through another one here. So I'm going to hide this. All right, now we're going to look at NH3 here. Okay, now first of all, you might be able to tell, in fact, I'm going to use a different color for NH3, because this is much more of an NH3-like color. There we go, this teal. What's different about this curve? Okay, this curve is decreasing as we increase temperature rather than increase like all the others, except for this one down here, and I'll explain this one later. NH3, when we try to dissolve it into water, okay, in this particular instance, it is a gas, and gases tend to dissolve less when you increase the temperature. And the way I want you to think about this is, let's say you put a 2-liter bottle of soda, okay, and you leave it in your car over the summer, okay, and you let it get all nice and hot. Okay, do you want to open it? You probably don't want to open it, because when you do, it's just going to go and spew all over the place. Okay, so we don't want to open it. Okay, why? Well, the reason why is that when the temperature has increased, the amount of dissolved gas decreases, which means, let's say we started up here, okay, this amount of gas is now no longer dissolved in our liquid, and so it's creating all of this pressure above the liquid, and as soon as you open it, okay, you have Spew City. That stuff just all over the place. Okay, so when you see a declining curve, you have one of two things happening. It is either you have dissolved a gas, or you have dissolved a really heavy solid. This down here is a huge molecule. It has a molecular mass of somewhere around 400, I think. When you're dissolving that in water, you'll get a little bit dissolve, but as you increase the temperature, the water molecules are going so fast, and the mass difference is so much, it's kind of like a bug hitting a windshield of a truck. And they run into it and bounce off, or they just run in, well, in this case, they run into it and bounce off. And all of the kinetic energy is passed back into the water molecules rather than passed into the solute molecule. And so it actually dissolves less. The water doesn't move the water isn't moving slow enough to allow for this giant molecule to dissolve into the liquid. So there's a little bit of common sense here. If you were to look at these two things, you see this has, what, 1, 2, that's 5 atoms there, times 3 is 15, 16, 17 atoms, and a total molecular weight of about 400 grams per mole. And this over here is 17 grams per mole. Which one of these do you think would be a gas? Which one of them do you think would be easier for it to exist with the oxygen and the nitrogen and stuff and the stuff that we breathe? They could be dissolved into a liquid and bubble its way out when it stops dissolving. It's not the heavy thing. The heavy thing, once it stops dissolving, is going to sink to the bottom because it's freaking heavy. This actually has, this is a very comparable molecular weight to water. And so if it's going to be a gas, if you're comparing these two, the NH3, the one with the lighter molecular weight, is probably going to be a gas. Okay, so let's work with our nitrogen here, though. Let's say you have, let's do a different question. We're going to use KNO3 over here. and you have 50 grams of KNO3 to dissolve. Your water is at 10 degrees Celsius to begin with, to begin the test. Okay, so the first question is, how much potassium nitrate is undissolved at the start? Okay, so imagine that you put all your KNO3 into your, we're going to have into 100 grams of water, right? Assume 100 grams of water. Okay. So we have 50 grams of KNO3. So here's our 50 grams. Okay, and we're at 10 degrees Celsius. Okay, and we're at 10 degrees Celsius. And where's the KNO3? That's this curve right here. Right? So how much do we have undissolved? Well, if we have 50 grams, but the KNO3 will only dissolve, 22 grams, 23 grams at 10 degrees Celsius, then the rest of it's going to be undissolved. So that's going to be, now let's make that a little brighter here. We have 50 grams minus the 23 grams that are dissolved is going to equal 27 grams of KNO3 that will be in excess. All right, so we're going to have that much stuff left undissolved. So now the question is, new question is, what temperature do we need? My handwriting is terrible today. I apologize, you guys. What temperature do we need to raise this solution? To what temperature do we need to raise the solution to dissolve all of your solute, all 50 grams? Okay, well, here's our KNO3. We have 50 grams. Okay, and we're going to go all the way to here, because at this point, this is where we have 50 grams dissolved. And what temperature is that? Oh, that looks to be about 34 degrees Celsius. Okay, there is one last situation that we need to go over that is a little more rare, but it happens sometimes, and you guys may have seen it if you've dealt with, say, like if you've ever made rock candy or something like that. Here's the situation. So let's say you dissolve a certain amount, and we're going to do this with our ammonium chloride here. And the ammonium chloride, let's say we start with right on this point right here. So we have 60 grams of ammonium chloride, and our solution is at 70 degrees Celsius. Well, it is possible to very slowly decrease the temperature, and as long as you don't disturb the solution or put any more solute into it, that as the temperature decreases, your solute stays dissolved in the solution. This is rare. Okay, it is difficult to do this, but it does happen, and it can get used sometimes for chemical purposes. But when you decrease the temperature, and all of a sudden you have the solute not falling out. It's not precipitating. It is staying dissolved. You create what's called a super saturated solution, or this is my oh, what the heck is that character's name? This is a particularly difficult word for me to say. It usually comes out as super saturated solution. But this is a rare situation, and we find out that this amount right here actually stays dissolved in the solution, and it just gets compacted as these solvent molecules get closer and closer together. The solute molecules find their places within the spaces between the solvent molecules, and they stay there, and they stay stuck in those positions, and they move with the rest of the solvent molecules, and they don't fall out, and they're kind of suspended in there. But this is a rare situation, and as soon as you add a little bit of solute crystal to that solution, it'll all fall out. And so you may hear supersaturated, and it's a really cool phenomenon. I'll show you guys a video of it. I'll post a video of it to Classroom so you guys can see it. But that is our third situation here. So we have a supersaturated solution. So we really have three. We have an unsaturated, okay, when it's less than maximum, then maximum. Okay, we have a saturated solution, which is at maximum. Okay, and this represents the solubility. Okay, so the solubility is the amount per 100 grams of water. And then there's supersaturated, which is actually greater than maximum. Okay, which logically doesn't sound right, but that's actually what happens, is that there should be a maximum amount under normal conditions, but these aren't normal conditions. These are very special conditions that allow this to happen. Okay, that should be enough to get you guys through your work for the next couple days, and if you have any questions, you guys know how to get a hold of me, and I will be in touch. Catch you guys later.